Tonight, I want to begin with a handful of real photographs, and two things about them that should not both be true. Here is the first. This is the Sun, our own star, seen up close by a spacecraft that watches it every hour of every day. Its surface churns at around 5,500 degrees Celsius, roughly 10,000 Fahrenheit. You can see the darker freckles of sunspots drifting across its face, each one a bruise wider than the Earth. And this is the Sun during a total eclipse, when the Moon slides in front of it and we can finally see the corona, the faint outer crown of gas that streams away from it into space. A single spacecraft, orbiting the Earth, stares at the Sun around the clock and sends back a picture like this every few seconds. Almost everything we know about our star's moods, its flares and its dark spots and its storms, comes from that one unblinking watch. Down in the core, where the light is actually made, the temperature reaches about 15 million degrees Celsius, something like 27 million Fahrenheit. It has been pouring out that heat and light in every direction for 4.5 billion years. Now here is the second photograph. This is the night sky, seen from the International Space Station, above the blur of our atmosphere. This is the view the crew get on the night side of every orbit, 16 times a day. That pale river pouring across the black is the Milky Way, our own galaxy seen edge on from the inside. Look how many stars there are, a few thousand of them scattered across the dark. It feels like the sky is full, but it isn't full. Between every bright point, there is a wide reach of pure black, far more black than light. And this is where it starts to come apart, because that darkness does not actually make sense. Here is the deepest photograph human beings have ever taken, made by staring at one dark, empty-looking scrap of sky for days on end. It is called the Hubble Ultra-Deep Field. At first it looks like a handful of colored specks scattered on black, but almost every one of those specks is not a star. It is an entire galaxy, a city of stars in its own right, and there are thousands of them crowded into this one small frame. We will come back to what that photograph really means. For now, just hold the sheer amount of light hiding in a patch of dark. Here is our nearest large neighbor, the Andromeda Galaxy, a single one of those islands, close enough to photograph in detail. And here is a newer eye still. The James Webb Telescope, looking in infrared, went deeper than Hubble ever could, and found galaxies so distant that their light set out when the universe was very young. Every fresh photograph we take, pointed anywhere at all, comes back crowded with light. The universe is not sparsely sprinkled with stars. It is drenched in them, in every direction, more of them than there are grains of sand on every beach and in every desert on Earth. So here is the question that has quietly troubled some of the finest minds in history for 400 years. If space goes on, and it is packed with stars in every direction, then no matter where you point your eye, your line of sight should eventually land on the surface of a star. And if every line of sight ends on a star, then the whole sky, every part of it, should be as bright as the face of the sun. The night should not be dark. The night should blaze. There should be no such thing as night at all. Something is holding the light back. Something is keeping the sky dark. And the answer, when we finally reach it, is one of the most beautiful ideas I know. But that is only the first of the two impossibilities. The second one is hiding in these same pictures, and almost nobody notices they are connected. The second impossibility is the cold. This is an astronaut, outside the spacecraft, on a spacewalk, with the sun shining full on the suit. You would think, with the sun right there, that space would be warm. And yet the side of that suit turned toward the sun is roasting, while the side turned away, in shadow, at the very same moment, is freezing hundreds of degrees colder. The same person, baking and freezing at once. We will see exactly how cold and why a little later. Here is the moon, photographed by the astronauts who stood on it. Look at the sky behind them. It is pure black, in the middle of the lunar day, with the sun blazing down. There is no air on the moon to soften anything. Here is its surface up close, the shadows knife-sharp, the craters hard-edged, and the sky above it black whether the sun is up or not. And here is our own world from space, the Earth, with that thin, bright rim of blue along its edge. That rim is the entire atmosphere, the whole thin skin of air that we live at the bottom of. Here is that same air seen edge-on from orbit, a thin band of blue and gold no thicker, in proportion, than the skin on an apple. Everything you have ever called weather or sky or a breath happens inside that sliver. That thin blue line is the only reason the ground beneath it is warm and the sky above it is bright. Take it away, and you get the moon. Daylight and a black, freezing sky. So the sun is a furnace beyond anything the word furnace can carry, pouring light across 93 million miles of space, about 150 million kilometers, and its light crosses that whole distance in a little over 8 minutes and arrives without weakening at all. And still, space is not warm. Space is brutally, almost unimaginably cold. If you floated out there in the sun's own light, the space around you would sit at about -270 degrees Celsius, only a few degrees above the coldest temperature that is physically possible anywhere, the sun shining directly on it, and colder than anything you have ever touched. 2 photographs. A sky drowning in the light of a trillion stars, and yet dark. A void with a furnace blazing in the middle of it, and yet freezing. And I want to show you, tonight, how those 2 facts are not just true side by side. They are the same fact, wearing 2 different faces, the same secret. And it is not really about darkness, and not really about cold. It is about time. Before we go anywhere, let me clear away one small confusion, because it trips up almost everyone. If space is so dark, you might ask, then how do the astronauts see any stars at all? How can they float up there and look out at a sky full of them, if the sky is supposed to be black? And the answer is a small hinge that a great deal of tonight will turn on. A star is a point of light. When you look at one, you are looking straight down a line that ends on its burning surface, and that light comes into your eye, and you see it. But the space between the stars is not lit up, because there is almost nothing out there to catch the light and scatter it back to you. Down here, in the daytime, the whole sky glows blue, even away from the sun, because sunlight is bouncing off the countless molecules of air over your head. Take the air away, and there is nothing left to do the catching. Each star's light flies straight past you in the dark, unseen, unless it is aimed right at your eye. So the stars are pinpricks of brightness floating in a blackness that swallows everything in between. Both things are true at once. The lights are real, and the dark between them is real, and there is no contradiction. Because the real puzzle was never why we can see a few thousand nearby stars. The real puzzle is why the spaces between them are dark. Why every one of those endless lines of sight, running out into a universe crowded with galaxies, doesn't end on a wall of fire. That is Olbers' paradox, and we will meet the people who wrestled with it, and the poet who guessed the answer, and the physicist who proved it. And the cold has its own story. Why the sun's heat crosses all that distance and still leaves the void frozen. Why an astronaut can bake and freeze in the same instant. Why there is a temperature, a specific, measurable temperature, that empty space simply will not go below, no matter how far you drift from any star. 2 ordinary facts. The sky is dark. Space is cold. The kind of thing a child could tell you. And underneath them, one of the deepest ideas we have ever had about where everything came from, and how old it all is, and why we are here to notice any of it. So settle in. There is nothing here you need to remember, nothing to follow closely. If your eyes drift shut somewhere in the middle, that is exactly as it should be. Let your shoulders drop. Let your breathing slow. And let's go and find out why the night is dark and why the light itself is cold. Let's begin with the brightness, because it is the thing you have known the longest, and it is not quite what it seems. When you stand outside on a clear afternoon, the whole sky is lit. Not just the sun, but the entire dome overhead, glowing a soft, even blue from one horizon to the other. It feels like the natural color of the sky. It feels like the color of space itself. It isn't. That blue is not out in space at all. It is happening in the thin skin of air just above your head, and it is a kind of trick of the light, in the most literal sense. Sunlight arrives at the top of our atmosphere as white light, which is really all the colors mixed together, from red at one end through to violet at the other. And as that light comes down through the air, it runs into countless molecules of gas, nitrogen and oxygen, unthinkably small and unthinkably numerous. When a ray of light meets one of these molecules, some of it gets knocked sideways, scattered off in a new direction. But here is the important part. The amount of scattering depends very strongly on the color of the light. The shorter, bluer wavelengths get scattered far, far more than the longer, redder ones. The effect is so steep that blue light is thrown around the sky many times more strongly than red. A physicist named Rayleigh worked out the exact rule for this in the 1870s, and the sky has been quietly obeying it for as long as there has been a sky. So the blue part of the sunlight gets bounced from molecule to molecule, scattered again and again, until it is coming at your eyes from every direction at once. You look up, away from the sun, and you still see blue, because that light has been ricocheting around the whole dome of the air to reach you. That is the blue of the daytime sky. It is not a thing. It is sunlight, caught and thrown around by the air. And the same rule paints the other end of the day. When the sun sits low at sunset, its light has to travel through a much longer slice of atmosphere to reach you, 20 or 30 times the thickness it passes through at noon. By the time it arrives, almost all the blue has been scattered away out of the beam entirely, and what is left is the deep red and orange and gold that we drive to the coast to watch. Sunrise, sunset, the blue of noon, all of it is the same story. Air, catching light. Now I want you to do something in your mind. I want you to take the air away. Imagine the whole atmosphere of the Earth simply gone, and you standing there in the vacuum in full daylight, the sun blazing away above you exactly as before. What happens to the sky? It goes black. Instantly, completely black, even with the sun right there. Because there is no longer any air to catch the sunlight and scatter it. The light still streams down from the sun, but it flies straight past you and off into space. And there is nothing left overhead to glow. You would be standing in bright sunlight, your own shadow sharp and hard at your feet, and above you, a sky as black as the deepest night, with the stars shining in it in broad daylight. You do not have to imagine this. You can go and look at the photographs. Because there is a world just next door where exactly this is true. The moon has almost no atmosphere at all, and so on the moon, the sky is black. Always. The astronauts who walked there stood in unfiltered sunlight, bright enough to wash out their cameras, and above them, the sky was pure, starless black. That black sky, by the way, is the innocent origin of a whole conspiracy theory. People look at the Apollo photographs, see the astronaut lit up by brilliant sunlight against a completely black sky with no stars in it, and decide it must be fake. Surely, they think, if it were real, the sky would be full of stars. But it is exactly the other way around. The black, starless sky is the proof that it is real. On an airless world in daylight, that is precisely what you should see. The sunlight on the astronaut and the ground is so overwhelmingly bright that the cameras, set to capture it, cannot also pick up the faint pinpricks of distant stars. And with no air to scatter any light, the sky itself has nothing to make it glow. A black daytime sky is not the mark of a hoax. It is the honest signature of a place with no air. The same is true across the solar system. On Mercury, which is a bare rock baking right next to the sun, the daytime sky is black. On Mars, which has only a wisp of an atmosphere, well under 1% as thick as ours, the sky is a pale, dusty butterscotch by day, and strangely, its sunsets glow blue, the mirror image of ours, because the fine dust there scatters light in the opposite way. On Venus, wrapped in a suffocating blanket of carbon dioxide 90 times heavier than our own air, you would see no sun at all, only a dim, even orange glow filtering through the clouds. Go further out, to Saturn's giant moon Titan, wrapped in a thick orange haze, and the sky is a dim, hazy tangerine, the sun reduced to a smudge of brightness with no disk at all. When a small probe descended to Titan's surface, that muddy orange gloom is exactly what it photographed. Each of these worlds has its own sky, painted by its own particular air, and not one of them looks like ours. And even here on Earth, the darkness of our own night is not perfectly black. There is a faint natural glow to the night sky, a whisper of light given off by the high atmosphere itself, so that a truly dark, moonless night is never quite as dark as empty space would be. The blackness we call night is already softened, just a little, by the same thin air that gives us our blue days. Pilots and astronauts have watched this happen with their own eyes. As you climb higher and higher, the air thins, and the blue overhead deepens and darkens and drains away, until near the top of the atmosphere, the sky above you has gone to black, even while the sun still blazes fiercely beside you. You do not fly up into the darkness of space. You fly up out of the brightness of the air. The blue was never very deep to begin with, only a thin, bright shell wrapped close around the ground, and once you rise above it, there is nothing left overhead but the black that was always there, patiently waiting behind the day. Every one of these skies is different, and every one of them is telling you the same thing. The color of a daytime sky is not a property of space. It is a property of whatever thin layer of air, or dust, or cloud that world happens to be wrapped in. The sky belongs to the planet, not to the cosmos. And it is the first time tonight that something we assumed belonged to the universe turns out to belong only to us, to our own particular thin envelope of air. It will not be the last. A great deal of what we take to be simply the way space is turns out, on closer inspection, to be only the way our own small corner of it happens to be dressed. Take the wrapping away, and underneath, everywhere, is the same black. And I think that is worth pausing on, because it quietly answers a question you might not have known you were asking. When we say the night sky is dark, we are looking through our own air, at night, when the sun is not lighting it up. But that darkness we see at night is only a pale hint of the real darkness. The genuine cosmic dark is what you would see in daylight on the moon. The blackness was always there, all around us, all the time. Our blue sky is just a curtain of scattered sunlight drawn across it every morning and pulled back every night. So the daytime brightness turns out to be local and thin and ours. It is not a feature of the universe. It is a feature of the air. And now here is where the two mysteries of tonight begin to lean toward each other, because that same thin layer of air does not only bring the light, it also holds the warmth. The blanket that scatters the sunlight into blue is the same blanket that traps the sun's heat close to the ground. Our atmosphere catches the sun's energy, holds on to some of it, spreads it around, evens it out between day and night. It is the reason the Earth does not roast on the sunlit side and freeze solid on the dark side every single day. The moon, with no such blanket, does exactly that. In the lunar day, the surface climbs to well over 100 degrees Celsius, hot enough to boil water many times over. And in the lunar night, in the very same spot, it plunges to around minus 170. No air to hold the warmth, no air to carry it from the lit side to the dark. The heat arrives, and then, the moment the sun is gone, it simply leaves. So the air does two things at once. It fills the sky with light, and it holds in the warmth. And when you take the air away, you lose both of them together. The sky goes black, and the world goes cold. That is the first hint that the darkness and the cold are not two separate problems. They are two symptoms of the same underlying thing, which is the emptiness of space itself. Which brings us to the real question, the one hiding under both of them. If the light and the warmth we know are really just gifts of a thin skin of air, then what is space actually like, underneath, when you strip all of that away? What is the true nature of the emptiness that our little blue blanket is stretched across? That emptiness is where the cold comes from. And to understand why the sun can be blazing right there and the void can still be freezing, we have to talk about what heat really is and what it needs in order to travel. So let's leave the sky behind for a while and go out into the vacuum itself and ask a simpler question than it sounds. In a place with almost nothing in it, what does it even mean to be cold? Here is a question that sounds almost too simple to ask. What is heat? Not where it comes from, not how we measure it, but what it actually is. When we say something is hot, what is the thing that is hot? The answer is motion. That is the whole of it, really. Everything around you is made of atoms and molecules, and those atoms and molecules are never still. They jitter, they vibrate, they rush about, they collide. And the temperature of a thing is simply a measure of how fast, on average, its atoms are moving. A hot cup of tea is a cup of water whose molecules are racing around and slamming into each other. Let it cool, and what is really happening is that the molecules are slowing down. Cold is not a substance that flows into the tea. Cold is just the absence of that motion. There is no such thing as cold in the way there is such a thing as heat. There is only more movement and less. Keep that firmly in mind, because it changes everything about what follows. Temperature is a property of matter in motion, and that means for something to have a temperature at all, there has to be something there, some stuff, some atoms to do the moving. Now think about empty space. Space is not perfectly empty, but it is closer to empty than anything we can make on Earth. In the space between the stars, there is, on average, about 1 atom in every cubic centimeter. 1. Compare that to the air you are breathing right now, where that same little cube holds something like 25 billion molecules, all crashing into your skin every instant. Space is emptier than the finest vacuum any laboratory has ever produced. And in a place that empty, the question, how hot is it, almost stops making sense, because there is barely anything there to have a temperature. But that emptiness is exactly what makes space so cold. And to see why, we need to talk about how heat gets from one place to another. Because it turns out there are only 3 ways, and space shuts down 2 of them completely. The first way is conduction. This is heat moving through direct contact, one jittering atom bumping the next, passing the motion along like a rumor through a crowd. Touch a hot pan, and the heat that leaps into your hand is conduction. It is fast, and it is powerful, but it needs a solid chain of matter to travel through. Take away the matter, and there is nothing to pass the motion along. The second way is convection. This is heat carried by a moving fluid, a liquid or a gas. Warm air rising off a radiator, hot water circulating in a pot, the wind carrying warmth from the sea. The heat rides along on the moving stuff, and again, it needs stuff. No air, no water, no fluid of any kind, and convection simply cannot happen. In space, both of these are dead on arrival. There is no solid chain of matter for conduction to run through. There is no fluid for convection to ride on. 2 of the 3 ways that heat travels are switched off entirely because both of them need a crowd of matter to work, and space is the emptiest place there is. That leaves only the third way, radiation. Radiation is heat that travels as light. Not visible light usually, but its invisible cousin, infrared. Anything warm glows in infrared, quietly pouring its heat out as radiation. Your own body is doing it right now. And unlike the other 2, radiation does not need any matter to travel through at all. It crosses empty space perfectly happily. That is how the sun's warmth reaches us across 93 million miles of vacuum in the first place. Pure radiation. There is a good way to feel the difference. Think of the beam of a flashlight cutting across a dark room. The beam is full of light, but it does not light up the empty air it passes through. You only see where it lands, on a wall, or a hand, or a drift of dust. Radiation in space is like that. The sun's energy streams outward as a river of radiation, but it does not warm the empty space it crosses. It only delivers its heat where it strikes something solid. A planet, a moon, the metal skin of a spacecraft, your face turned up toward it. The space right beside the sun is not warm because there is almost nothing out there for the radiation to warm. The heat is in the sunlight, not in the space, and the space stays cold until the light finds something to land on. So here is the strange, lonely situation you find yourself in, out in space. The only way you can gain heat is by radiation landing on you, mostly from the sun. And the only way you can lose heat is by radiating it away yourself, into the dark. There is no air to warm you, and, just as importantly, no air to insulate you. You are a small, warm thing, glowing away your own heat into an almost infinite cold sink, with nothing around you to slow the loss. And now I can tell you why an astronaut on a spacewalk lives in the strangest thermal world of all. When an astronaut steps outside their spacecraft into direct sunlight, the sunlit side of their suit can climb to around 120 degrees Celsius. That is 250 Fahrenheit, well past the boiling point of water. And at the very same moment, the side of their body turned away from the sun, sitting in shadow, can fall to around minus 157 Celsius. Minus 250 Fahrenheit. One person, one suit. Baking on one side and freezing on the other at the same instant, with a difference of nearly 300 degrees across their own body. And this can flip in minutes, because the space station is racing around the Earth once every 90 minutes or so, passing from blazing sunlight into the planet's shadow and back again, over and over, 16 sunrises and 16 sunsets in a single day. There is no gentle warmth out there, no even temperature to settle into. There is only the fierce, direct beam of the sun on one side, and the endless cold of empty space on the other, and nothing in between to soften either one. The air that we never think about, the air that spreads warmth around and evens it out and makes a summer afternoon feel mild, simply isn't there. So how does the astronaut survive it? The answer is a small marvel of engineering, and it is the same idea as something sitting in your kitchen right now. A spacesuit is, in effect, a tiny, one-person spacecraft. Its outer layers are white, to reflect away as much of the sun's fierce light as possible, and it is built from many thin layers with vacuum and reflective foil between them, so that heat can neither pour in nor leak out too quickly. And woven against the astronaut's own skin is a garment threaded with nearly 1,000 feet of narrow tubing, through which cool water is constantly pumped, carrying away the heat of their own working body, so they do not overheat inside their insulated shell. The suit, in other words, is a thermos, and that is not a metaphor. It is exactly the same principle. There is something counterintuitive hiding in all of this. You might think the great danger of space is the cold, that the whole problem is staying warm. But for a working spacecraft, the harder problem is very often the opposite. A craft in sunlight, packed with electronics all quietly generating heat, has no air around it to carry that heat away, no breeze, no cool atmosphere to bleed it into. The heat just builds and builds, with nowhere to go. And so, a spacecraft like the space station carries enormous radiators, great panels whose only job is to face the dark and glow their excess heat away as radiation, because radiation is the single escape route left. In the emptiness, getting rid of warmth can be just as hard as holding on to it. The void does not simply freeze you. It refuses to take your heat on any terms but its own, slowly, through radiation, and no other way. Think about a good thermos flask, the kind that keeps coffee hot for hours. If you look at how it is built, it is a bottle inside a bottle, and between the two walls there is a vacuum, a thin gap with the air pumped out. That vacuum is the whole secret. Because heat cannot conduct across empty space, and it cannot convect across empty space, the vacuum gap chokes off 2 of the 3 ways your coffee could lose its warmth. The only route left is radiation, and they line the walls with a mirror-bright silver coating to bounce even that back inside. A man named James Dewar built the first one of these in 1892 in a laboratory to keep things cold, and it works so well that we have been carrying it around in our lunchboxes ever since. Here is what I find quietly wonderful about that. A thermos keeps your coffee hot by wrapping it in a little piece of outer space. That gap of vacuum between the two walls is doing, on a small scale, exactly what the emptiness of space does on the largest scale. It stops the heat from traveling because there is nothing there to carry it. And so the coldness of space starts to look less like some active, hostile force and more like a kind of profound loneliness. Space is not cold because it is full of some freezing substance. Space is cold because it is empty. Because a warm thing placed out there has almost no way to hold on to its warmth, and every way to lose it, radiating quietly away into a dark that never gives anything back. The sun can be right there, blinding and enormous, and still the void stays frozen, because heat needs a crowd to travel through, and space is the loneliest place there is. But that raises a sharper question, and it is the one that is going to crack this whole story open. If space is so empty, and a warm thing out there just keeps radiating its heat away into the dark, then how cold does it actually get? How far down does the temperature go? You might expect the answer to be simple. All the way down. To the very bottom. To absolute zero. The coldest anything can possibly be. But that is not what happens. And the reason it is not what happens is the first real clue to the secret that ties this whole night together. Let's go back to what temperature really is, because it leads somewhere remarkable. If heat is the motion of atoms, then cold is those atoms slowing down. And that immediately suggests a question. What happens if they slow all the way down? What if you kept cooling something, drawing out its heat until its atoms stopped moving altogether? That point exists. It has a name. We call it absolute zero, and it is the coldest temperature there can ever be, anywhere, for anyone. It sits at minus 273.15 degrees Celsius. In Fahrenheit, minus 459.67. At absolute zero, the jittering stops. The motion that we call heat falls as low as the laws of physics will allow. You cannot go any colder, because there is no such thing as less than no motion. It is the true floor of the universe, the bottom of the temperature scale, the place where cold runs out of room. We measure temperature up from that floor for a reason, and it is why scientists so often count in Kelvin, a scale that begins at absolute zero itself. 0 Kelvin is the very bottom. On that scale, water freezes at 273 degrees and boils at 373. And empty space, as we are about to see, sits at just under 3 Kelvin, almost all the way down, but not quite. That little gap, that not quite, is where the whole secret of tonight is hiding. Now, we have never quite reached it, and in a deep sense we never can. But in laboratories on Earth, physicists have crept astonishingly close, cooling tiny clouds of atoms to within a billionth of a degree of absolute zero, colder than anywhere in nature, colder than the depths of space. At those temperatures, matter starts to behave in strange and beautiful ways that have no place in our warm, everyday world. But that is a story for another night. And yet, for all our cleverness, we cannot make anywhere on Earth as reliably, permanently cold as the empty depths between the stars. Our record-breaking cold lasts a fraction of a second in a sealed chamber at enormous effort and expense. The cold of deep space is simply there, everywhere, all the time, for free. Which makes you wonder how we even know its temperature. We cannot exactly hang a thermometer out in intergalactic space, but we do not have to. Every direction we turn our most sensitive instruments, we pick up the same faint hum of energy, the same gentle warmth, holding at the same value. Turn the instrument any way you like, and the emptiness reads back the same small number. 2.7 degrees, in every direction, to a remarkable precision. That sameness in every direction is itself a profound clue, and we will come to what it means. For now, just hold the strangeness of it. There is a single temperature, the same everywhere across the entire observable universe, and nothing natural ever falls below it. It is worth pausing on how hard-won cold really is. Down near absolute zero, in those laboratory experiments, matter stops behaving the way it does anywhere in ordinary life. Atoms lose their separate identities and merge into a single shared state. Liquids begin to creep up the walls of their containers and flow without any friction at all. Electricity runs through certain metals with no resistance whatsoever, on, forever. The deep cold is not a dead, empty nothing. It is a doorway into some of the strangest physics we know, and reaching it takes staggering effort. Elaborate machines cooling atoms with lasers and magnets, fighting for every last fraction of a degree. Real cold, it turns out, is expensive. Warmth is the thing that comes for free when you happen to have a star nearby, which is one more small reason that the warm, lit world you are lying in tonight is rarer and more precious than it ever feels. What I want to ask tonight is this. Out there in the real universe, in the empty space between the stars, far from any sun, how close does nature get to absolute zero on its own? We just spent the last part of this journey watching a warm object in space radiate its heat away into the dark, with almost nothing around to give any warmth back. So you might reasonably think that the deep emptiness, out where no star is shining on you, should sink all the way down, right to the bottom, to absolute zero, or a whisker above it. It doesn't. Go out into the darkest, emptiest stretch of space you can find. Get as far from any star as you like. Turn away from every source of heat. And the temperature there does not fall to absolute zero. It stops, and it holds, at about 2.7 degrees above absolute zero, around minus 270 degrees Celsius. It will not go lower, no matter how far into the void you travel. 2.7 degrees, not zero. It sounds like almost nothing, and in a way it is almost nothing, a faint whisper of warmth just above the absolute floor. But it is not nothing. And the difference between 2.7 and zero is one of the most important gaps in all of science, because something is keeping it there. Think about what that means. If space were truly perfectly empty, if there were nothing out there at all, then a thing left alone in the deep dark should just keep radiating its heat away until it reached absolute zero and stopped. There would be nothing to hold it up. But it does get held up. Everywhere in the universe, in every direction, the emptiness sits at that same faint 2.7 degrees. There is a floor under the cold, and it is not at the bottom. It is a little way up, which can only mean one thing. Space is not truly empty of warmth. There is a faint heat that fills all of it, a gentle, even glow of energy that soaks through every cubic inch of the cosmos, from here to the farthest galaxy, keeping the whole universe at that same small temperature above absolute zero. Something is out there, filling everything, glowing ever so slightly, and nowhere, no matter how remote, ever gets colder than the warmth it provides. I want you to hold that image, because we are going to come back to it. And when we do, it is going to turn out to be the single most important thing in this entire story. There is a faint glow that fills the universe. Remember that. It is going to be the answer to a question we haven't even properly asked yet. But first, let me show you just how strict that floor is. by telling you about the one place in the entire known universe that breaks it. Because the exception, as often happens, tells you more than the rule. If 2.7 degrees is the natural temperature of empty space, held up by that faint universal glow, then you would think nothing could ever be colder. And almost nothing ever is. But there is a single object out there that we know of that has found a way to dip below it. It is called the Boomerang Nebula, about 5,000 light-years away in the southern sky. At its heart is a dying star, and that star is throwing off its outer layers in an enormous, fast wind, gas rushing outward at nearly 600,000 kilometers an hour. And here a simple piece of physics takes over, the same physics that makes the air hiss cold out of an aerosol can when you spray it. When a gas expands very fast, it cools. The Boomerang Nebula is expanding so violently and so fast that it has chilled its own gas down to about 1 degree above absolute zero. 1 degree. Which means, extraordinarily, that this little patch of dying star is colder than empty space itself. It is colder than the faint universal glow that holds up the temperature everywhere else. It is, as far as we know, the coldest place in the entire universe. The one spot that has managed to sink below the floor that the rest of the cosmos rests on. Astronomers found it in 1995, and it still holds the record. And I love that it exists because of what it proves. It proves that the 2.7 degrees really is a floor, a real, physical thing you have to actively fight against to beat. The Boomerang Nebula had to spend the enormous energy of a dying star, blasting its gas outward at close to 600,000 kilometers an hour, just to get a single degree below the level that the empty universe sits at for free. Everywhere else, that faint glow wins. Everywhere else, the cold cannot get past it. So let me gather up where we are, because we have quietly assembled half of a mystery. The cold of space, we now understand, is not some active force. It is emptiness. A warm thing out there loses its heat because there is nothing to carry the warmth and nothing to insulate it, only the slow radiation of its own glow into the dark. Left alone, it should fall all the way to absolute zero. But it doesn't. It stops at 2.7 degrees because the whole universe is filled with a faint, even warmth that will not let anything, anywhere, get colder than that. A glow with no obvious source, soaking through all of space, exactly the same in every direction you look. And I have told you to remember that glow, because we are about to walk away from the cold entirely and go and look at the other mystery, the dark night sky. We are going to spend a long while over there, with old astronomers and a poet and a paradox 400 years in the making, and it is going to feel like a completely separate story. And then, near the very end, that faint glow filling all of space is going to walk back into the room. And you are going to realize that it was never a separate story at all. That the thing keeping the void at 2.7 degrees and the thing keeping the night sky dark are one and the same. The same glow, the same secret, the same ancient light. But I am getting ahead of myself again, and there is no need to rush. Let the cold settle for now, at 2.7 degrees above the bottom of everything, held up by a warmth we cannot yet explain. And let's turn our eyes instead to the dark, to the oldest and simplest question in the sky, the one a child asks and no one could answer for 400 years. Why, when the universe is full of stars, is the night sky black? Some questions are so simple that it takes a genius even to notice they are questions at all. Why is the night sky dark? A child might ask it and be told, because the sun has gone down. And that answer feels complete. But it isn't. And a handful of remarkable people across 4 centuries saw that it isn't and could not let it go. Let me build the puzzle up carefully, the way they did, because it is one of those ideas that seems obvious right up until the moment it becomes impossible. Start with a single star. Its light spreads out in all directions as it travels, so the farther away a star is, the fainter it looks to us. A star twice as far away looks 4 times fainter. 3 times as far, 9 times fainter. The brightness falls off very quickly with distance. This is just the plain geometry of light spreading out into space, and it is why distant stars are dim. So far, so reasonable. Faraway stars are faint. That seems like it should help explain the darkness. But now think about how many stars there are at each distance. Picture a thin shell of space around us, like the skin of a bubble at some great distance. Because that shell is so far out, it is enormous, and it holds a huge number of stars. And here is the crucial thing. A shell twice as far away is bigger, so it holds more stars. 4 times as many, in fact. But each of those stars, being twice as far, looks 4 times fainter. So you have 4 times the stars, each giving a quarter of the light. More stars and dimmer light, in exactly the same proportion. The two cancel out perfectly, and that distant shell delivers the very same total glow as the near one. Do you see what that means? Every shell of sky, near or far, contributes the same total amount of light. The nearby shell has a few bright stars. The distant shell has vastly more, but fainter, stars. And it all adds up to the same. And if the universe goes on forever, there are infinitely many such shells, each adding the same amount of light, one after another, without end. Add up an endless number of shells, each contributing its share of light, and the total is not just bright, it is infinite. The whole sky, in every direction, should be blindingly, uniformly bright as the surface of a star. There is another way to see the same thing, and it is even more vivid. Imagine you are standing in the middle of an infinite forest, not a large forest, an endless one, with trees scattered evenly in every direction, forever. Now look out horizontally, between the trunks. Close to you, there are gaps you can see through. But as your gaze travels outward, there are more and more trees, and every possible line of sight, no matter how narrow the gap it starts through, must eventually run into a trunk somewhere out there in the endless woods. You cannot see out. In every direction, near or far, your eye lands on wood. The whole horizon becomes a solid wall of trees. Now swap the trees for stars, and the forest for the universe. In an infinite cosmos evenly filled with stars, every single line of sight, followed far enough, must end on the surface of a star. There are no permanent gaps. The whole sky should be a solid, seamless wall of starlight, as bright as the sun, everywhere, all the time, day and night. It is hard to overstate how violent that prediction is. We are not talking about a sky a little brighter than the one we see. We are talking about a sky in which there is no need for a sun at all, because every point overhead, in every direction, would already be shining with the full brilliance of a stellar surface. There would be no darkness to rest your eyes in, no night to sleep through, no shadows anywhere, nowhere on the surface of any world that was not being roasted from every side at once by an entire sky on fire. The earth, and everything on it, would have been burned away long ago. The gentle scattering of stars we actually see, floating in a calm ocean of black, is about as far from that blazing prediction as it is possible to get. That is the paradox. In an infinite, ageless universe full of stars, there should be no darkness anywhere. The night sky should blaze, and yet you have seen the night sky. It is black, with a scattering of stars and vast reaches of nothing in between. The prediction and the reality could not be further apart. Something is deeply, fundamentally wrong with the simple picture of an infinite, eternal, star-filled universe. The darkness overhead is quietly telling us so, every single night, and has been for all of human history. It took a long time for anyone to hear it. The first person we know of who even glimpsed the shape of this was an Englishman named Thomas Digges, back in the 1500s. He was among the first to imagine the universe not as a small, closed box of crystal spheres, the way the ancients had, but as something that might stretch out infinitely, scattered with countless stars. A beautiful, bold idea. But an infinite universe of stars carries this hidden problem inside it, and Digges did not quite catch it. It is worth remembering how dangerous this idea once was. To imagine the universe as infinite, scattered endlessly with other suns, was to unseat the earth from the center of creation altogether, and that was not a safe thing to think. Around the same period, the Italian philosopher Giordano Bruno argued for exactly such a cosmos, countless suns with countless worlds turning around them, and it was among the beliefs that led to his being burned at the stake in the year 1600. The infinite universe was not merely a puzzle. It was, for a time, a heresy, and folded quietly inside it, waiting, was this paradox of the dark, a problem the boldest thinkers of the age were only beginning to sense. The one who first really posed the question was Johannes Kepler in 1610. Kepler is one of the giants, the man who worked out how the planets truly move. And when he considered the idea of an infinite universe full of stars, he saw the trouble at once. The sky is dark, he reasoned. If the universe were infinite and full of stars, it would not be. Therefore, he concluded, the universe must not be infinite. There must be an edge, a dark wall enclosing the stars. For Kepler, the darkness of the night was proof that the cosmos was finite and closed. It was the wrong conclusion, as it turned out, but it was the right thing to be troubled by, and he was troubled by it 4 centuries ago. Over the next century, others circled the same puzzle. The great English astronomer Edmund Halley, the one the comet is named for, took it up around 1720 and wrestled with it in front of the Royal Society. A Swiss astronomer named Jean-Philippe de Chéseaux worked on it carefully in 1744, and he was the first to propose a specific way out. Perhaps, he suggested, there is some thin material spread through space, some faint fog, that absorbs the light of the most distant stars before it can reach us, and that is why the far reaches of the sky are dark. It was a natural idea, and, as we will see, it was wrong, for a reason that is beautiful in its own right, and that ties straight back to everything we just learned about heat. What strikes me about this whole stretch of history is how many good minds circled the same flame without quite catching it. Halley stood before the Royal Society and turned the puzzle over out loud. De Chéseaux filled careful pages with it. Each of them felt the wrongness of a dark sky and an infinite universe, and each reached for the nearest handhold and missed. What they were all missing was not more cleverness. It was a piece of physics that had simply not been discovered yet, and would not be, for a very long time. And then, in 1823, a German astronomer named Heinrich Wilhelm Olbers wrote it all up again. Olbers was a physician by profession and an astronomer by passion, the kind of dedicated amateur who did real science in the hours after his patients had gone home. He laid out the paradox clearly, and he reached for the same escape de Chéseaux had, the idea of absorbing matter in space, soaking up the distant light. And for reasons that have as much to do with the accidents of history as with the merit of the work, it is Olbers' name that stuck. To this day, we call it Olbers' paradox, the dark night sky paradox, carrying the name of one man among many who puzzled over it. I want to be honest about that, because I think the honesty is part of the beauty. Olbers was not the first to notice it. He was not even close to the first. Kepler saw it 200 years earlier. De Chéseaux gave essentially the same answer Olbers gave, decades before him. The historian who untangled all of this, a physicist named Edward Harrison, was quite direct about it. Olbers was far from the first, and his particular contribution was not especially valuable. And yet, the name endures, the way names sometimes do, attached a little unfairly to a puzzle that belonged to many minds across many lifetimes. So let us call it Olbers' paradox, as everyone does, while remembering that it is really the paradox of 400 years of people looking up at the same dark sky and refusing to accept the easy answer. Refusing to say, the sky is dark because the sun went down, and insisting instead on the harder, stranger version of the question. Why? In a universe full of stars, is there any darkness at all? They had the question. What they did not yet have was the answer. And the answers they reached for, the fog, the absorbing matter, the closed wall at the edge of the cosmos, were all, one by one, going to fail. Because it turns out, you cannot make the darkness by hiding the light. The universe will not let you. And the reason the fog does not work is going to bring us straight back to the heat we thought we had left behind. So let's take each of the wrong answers in turn and watch them fall. Because in watching them fall, we are going to be pushed, with no other way out, toward the truth. There is a particular pleasure in watching a wrong answer fail, when it fails for a deep reason. It is one of the ways science actually moves forward. You try the obvious thing, and the universe quietly shows you why it cannot be so. And in the ruins of the obvious thing, you find a clue to the truth. So let us take the wrong answers to the dark sky paradox, one at a time, and watch them go. The first and most natural wrong answer is the one de Chéseaux reached for, and Olbers after him. The idea that space is not perfectly clear, that somewhere out there, between us and the most distant stars, there is some thin material, dust or gas or fog, that soaks up the light of the far-off stars before it can ever reach our eyes. The nearby stars we see, the distant ones are veiled, and so the sky is dark. It feels almost obviously right. And it is wrong, for a reason that is beautiful, and that brings us straight back to the heat we spent the first half of tonight learning about. Think about what happens to that dust if it sits there, year after year, century after century, soaking up starlight. The starlight carries energy. If the dust absorbs that energy and does nothing with it, it must get warmer and warmer. A thing that keeps absorbing energy without limit does not stay cool and dark. It heats up. But we already know what a warm thing does. It radiates. Everything with a temperature glows, pouring its heat back out as light. So the dust, bathed for ages in the light of countless stars, would heat up until it was glowing just as brightly as the starlight falling on it. It would reach what we call thermal equilibrium, taking in exactly as much light as it gives off. And at that point, it stops hiding anything at all. The dust does not swallow the starlight and stay dark. It absorbs the starlight and then shines with it, glowing as fiercely as the stars themselves. Put the fog in the way, and the fog catches fire. You have not darkened the sky. You have simply added one more glowing thing to it. The darkness survives the dust, because you cannot make a place dark by filling it with something that will only heat up and glow. It was Lord Kelvin, right at the start of the 20th century, who made this argument sharp and unanswerable, and we will come back to him properly in a moment, because he did far more than knock down the dust. But this piece alone was enough to kill the oldest answer. The very heat that we learned about earlier, the fact that anything warm must radiate, reaches across and destroys the idea that hidden matter could ever explain the dark. The two halves of tonight's story are already starting to touch. I want to linger on that for a second because it is the first place where the cold and the dark reach across and shake hands. The reason you cannot hide the stars behind a curtain of dust is the very same reason a warm thing in space cannot stay warm. Everything with a temperature radiates. Absorb energy, and you must eventually give it back as light. That single, simple law, the one that governed everything we said about heat, turns out to also stand guard over the darkness of the sky, quietly forbidding the easiest way out of the paradox. The same thread runs through both halves of the night, and this is the first place you can feel the knot in it. So the fog fails. On to the second wrong answer. Perhaps, you might say, the universe simply runs out of stars. Perhaps there is a great sphere of stars around us, and beyond it, nothing. just empty blackness. The lines of sight that don't happen to hit a star within that sphere would then run out into the void and end on nothing, and those would be the dark patches between the stars. A universe with an edge. A finite island of light in an endless dark. This was, in a sense, Kepler's answer 400 years ago, and it is a reasonable guess. But the more we have looked, the more clearly it has failed. Because every time we build a bigger telescope and look deeper into the dark patches between the stars, we do not find an edge, we find more. Point our finest instruments at a piece of sky that looks utterly black and empty. Hold the exposure open long enough, and that black patch fills with galaxies. Not stars, galaxies. Each one a city of 100 billion suns, thousands of them crowded into a speck of darkness the size of a grain of sand held at arm's length. The famous deep field images from our great space telescopes did exactly this, and every one of them tells the same story. The deeper we look, the more there is. There is no sign of a wall, no edge where the stars stop. The universe is vast beyond our ability to see the end of it, and it is full of light the whole way out, as far as we can reach. There is one image I keep coming back to. In 2004, astronomers pointed the Hubble Space Telescope at a single tiny patch of sky, chosen precisely because it looked utterly empty, a speck of pure black about 1/10 the width of the full moon. They held the exposure open for the equivalent of 11 days, patiently gathering the faintest trickle of light. And that black, empty speck filled with around 10,000 galaxies. 10,000. In a scrap of darkness you could hide behind a grain of sand held at arm's length. Every one of them, a vast island of hundreds of billions of stars, and many so far away that their light had been crossing space toward us for more than 13 billion years. If the darkest sliver of sky we can find holds 10,000 galaxies, then looking deeper does not ease the paradox. It makes it overwhelming. There is more than enough light out there to fill the whole sky many times over. The only question left is why it does not arrive as a blaze. So we cannot escape the paradox by running out of stars. There are more than enough stars, more than enough galaxies, going far enough out to fill every line of sight many times over. The edge is not the answer. If anything, looking deeper has made the paradox worse, not better. The sky should be more blazing, not less. Which brings us to the third wrong answer, the cleverest of the three. Perhaps the stars are not spread evenly through space, but clumped in a special way. We know stars gather into galaxies, and galaxies into clusters, and clusters into greater structures still. What if that clumping goes on forever, in a particular pattern, thinning out on the largest scales in just such a way that the light never quite adds up to infinity? A cosmos arranged so cunningly that the gaps between the clumps always win, and darkness leaks through. It is a subtle idea, and for a while it was taken seriously. But as we mapped the universe on the grandest scales, we found that it does not work that way. Yes, there is structure. Stars in galaxies, galaxies in clusters, clusters strung along vast filaments with great empty voids between them, a cosmic web of breathtaking size. But if you pull back far enough, far beyond any single filament or void, the universe smooths out. On the very largest scales, it is remarkably even, the same in every direction, no special thinning pattern that could rescue us from the paradox. The clumping is real, but it is local, and it does not go on forever in a way that would save the darkness. There is one more effect I should mention, because it is real, and it does help, though it is not the whole answer either. The universe is expanding, and as we will see later, that expansion stretches and weakens the light of the most distant sources, draining energy from it, shifting it toward the red and beyond. So even the light that does reach us from very far away arrives dimmed and cooled by the long journey. That is a genuine part of why the far universe is not blinding, but on its own it is not enough to make the sky dark. It only softens the blaze. The real weight of the answer lies somewhere else entirely, in something none of these fixes even touched. So the third answer fails too. The stars are not hidden by fog, because the fog would only glow. They do not run out at some edge, because the deeper we look, the more we find. And they are not arranged in some sly pattern that lets the dark leak through, because on the largest scales, the universe is smooth and even. Every attempt to make the sky dark by rearranging the stars or by hiding their light has failed. And each failure has quietly narrowed the possibilities until there is really only one door left standing. Notice what all three of the wrong answers have in common. Every one of them tried to solve the problem in space, by adding stuff to space, or putting an edge in space, or clumping the stars in space. They were all answers about where the stars are and what lies between them. But the darkness of the night sky is not a problem about space. It never was. And that is the thing that took 400 years to see. Kepler could not see it. Halley could not see it. Chéseaux and Olbers could not see it, because the answer was hiding in a place none of them thought to look. And there is a lesson in that failure worth keeping. Every wrong answer here was a good answer to a different question. Dust really does dim starlight over short distances. The universe really is clumped into galaxies and clusters. Expansion really does redden the most distant light. None of these ideas was foolish. They were all true, and all beside the point, because they were all answers about how the stars are arranged in space, and the darkness of the sky was never, at bottom, a question about space at all. The answer was in time. Not where the stars are, when they are. Not how far the light has to travel, but how long it has had to travel. The whole paradox dissolves the moment you stop asking about the size of the universe and start asking about its age. And the astonishing thing, the thing I find almost moving, is that the first person to say this clearly was not an astronomer at all. He was a poet. A troubled, brilliant, dying poet who wrote it down 1 year before the end of his life in a strange and beautiful book that almost no one took seriously at the time. Let me tell you about him. His name was Edgar Allan Poe. You almost certainly know him, but not for this. You know him for the telltale heart beating under the floorboards, for the raven at the chamber door, for tales of dread and grief and the strange machinery of the human mind. Poe more or less invented the detective story and did as much as anyone to shape the horror story. He was a poet and a critic and a haunted man, and his life was hard and often sad, and it was nearly over when he did the thing I want to tell you about. In 1848, 1 year before he died, Poe published a long, sprawling, difficult work he called Eureka. He described it as a prose poem, and also as a serious account of the universe, its origin, and its destiny. Most of his contemporaries did not know what to make of it. Some thought it the ramblings of a man in decline. It sold poorly. It was, by most measures, a failure. And buried inside it, almost in passing, Poe wrote down the answer to a paradox that had defeated Kepler and Halley and every astronomer for 200 years. He was thinking about exactly our problem. The stars, he wrote, should fill the whole sky with light, and yet the sky is mostly dark. And then he offered his solution, and I want to give you the shape of it as closely as I can, because it is so nearly perfect that it is hard to believe a poet with no telescope wrote it. The only way, Poe reasoned, that we could see darkness between the stars, in a universe that surely contains them without number, is if the light from the most distant stars has simply not yet arrived. Light, he understood, travels at a finite speed. Fast, yes, but not infinite. It takes time to cross space. And so, if the universe itself has not existed forever, if it had a beginning a finite time ago, then the light from the farthest stars has not had long enough to reach us. It is still on its way. And where that light has not yet come, we see the dark. Read that again slowly, because of what it contains. Poe is saying that the darkness of the night sky is not empty space. It is the part of the universe whose light is still traveling. The dark patches are not places where there are no stars. They are places whose starlight has not had time to get here yet. And for that to be true, the universe must be young enough that light has not had time to cross it. The universe, Poe is saying, must have a birthday. This is the answer. Not the fog, not the edge, not the clumping. Time. The night is dark because the universe is not infinitely old, and light is not infinitely fast, and so there simply has not been enough time for the whole sky to fill with light. A poet wrote that, in a book almost no one read. A year before he died in poverty and confusion in a hospital in Baltimore, he reached out with nothing but reason and imagination and touched one of the deepest truths about the cosmos, decades before the science could catch up to him. It is genuinely stirring. It is one of my favorite moments in the whole history of ideas, precisely because it came from the person you would least expect, working in the medium you would least expect, at the worst moment of his life. Poe's own life gave out the following year. In October of 1849, he was found delirious on the streets of Baltimore and died a few days later in a hospital, only 40 years old, the exact circumstances still a mystery to this day. He never knew what he had done. He never knew that the strange, unread book of his final year held an idea that science would take another 50 years to confirm. Eureka was dismissed in his lifetime and half forgotten after his death. And the quiet tragedy of it is that if the poet had been believed, if anyone had taken him seriously, we might have understood the dark sky decades sooner. But great ideas do not always arrive with the right credentials, and the world is slow to hear a writer of horror stories explaining the origin of the cosmos. And Eureka reached even further than the dark sky. In its strange, rushing pages, Poe imagined a universe that had sprung from a single original unity and was still unfolding outward from it. A cosmos with a beginning and a history and a direction in time. He had no evidence, no equations, only intuition and nerve. And much of the detail was wrong, as it had to be. But the central instinct, that the universe was not a static, eternal stage, but something that began and aged and grew, was decades ahead of the science. And it is the very same instinct that turned out to hold the key to the dark. Now, to be fair, Poe's version was a vision, not a proof. He sketched the right idea in bold, poetic strokes, but he did not have the mathematics or the physics of stars to make it rigorous. He could not have. The tools did not exist yet. It would take another half a century and a very different kind of mind to turn the poet's insight into hard science. That mind belonged to William Thomson, better known to history as Lord Kelvin. Kelvin was one of the towering physicists of the 19th century, a man so central to the science of heat and temperature that we named the scale of absolute temperature after him. Every time tonight that I have said something sits at 2.7 Kelvin, or that absolute zero is 0 Kelvin, I have been using his name. He understood heat as deeply as anyone who has ever lived, and in 1901 he turned that understanding on the dark sky paradox and finished what Poe had begun. Kelvin did two things. First, he drove the final nail into the idea of the absorbing fog, with exactly the argument we met a moment ago. He understood, better than anyone, that matter which absorbs light must heat up and glow. So he showed, rigorously, that no amount of intervening dust could ever keep the sky dark, because the dust would simply come to shine as brightly as the stars. That door he closed for good. And then he did the harder thing. He took the idea of a finite age, Poe's poetic insight, and he made it into real, quantitative physics. He asked the question properly. Given how bright stars are, and how far apart they are, and how long a star actually lives before it burns out, how long would it take for enough starlight to accumulate to fill the sky? And how long has there actually been light in the universe? When he worked it through, the answer was stark. Stars do not live forever. They shine for a while and then they die. And the universe simply has not existed long enough, and the stars do not live long enough for their combined light to ever build up into that blazing wall the paradox predicted. There has not been enough time. The light that would be needed to fill the sky is still out there in transit, or was never emitted at all, or belongs to stars that have already burned out. The sky is dark because the universe is young, and light is slow, and stars are mortal. To feel the force of what Kelvin showed, think about what it would actually take to fill the sky. You would need the light of an unbroken wall of stars, stacked out to infinity, every one of them shining steadily for the entire history of the universe. But stars are not eternal. Each one burns for a while, a few million or a few billion years, and then it dies. And there has simply not been enough time, since there was any starlight at all, for the light of enough stars to pile up and fill the gaps, and the stars keep burning out before they can. The sky cannot fill because the universe is too young and the stars are too short-lived. Work the numbers, as Kelvin did, and the darkness stops being a mystery. It becomes something the universe cannot avoid. Kelvin's resolution was correct in its essentials, and it was rigorous, and it should have been famous immediately. But like Poe's, it was strangely overlooked for decades, tucked away in a paper few people read. It took later astronomers, digging back through the history, to rediscover what Kelvin had done and give him his due. It was the great astronomer Harlow Shapley, among others, who helped carry the finite age resolution into the mainstream, and later Harrison, who traced the whole tangled lineage back through Kelvin and Poe to Chéseaux and Kepler and beyond. The historian I mentioned earlier, Edward Harrison, was the one who finally pieced the whole story together and made clear that the answer had been there, essentially complete, since 1901, and in poetic form since 1848. So here is where we have arrived. The darkness of the night sky, that simplest of childhood observations, turns out to be evidence, hard evidence, that the universe had a beginning, that it is not infinitely old, that there was a time before which there was no starlight at all, and that not enough time has passed since then for the light to fill the sky. The dark between the stars is not empty, it is young. It is the part of the universe whose light is still on its way to us, and may not arrive for a very long time, and some of which will never arrive at all. And that is an astonishing thing to be able to read off the sky just by noticing that it is dark at night. You do not need a telescope. You do not need any instrument at all. You just need to stand in your own back garden, look up, see the darkness, and understand what Kepler and Halley and Olbers could not, and what Poe and Kelvin finally did. That the darkness itself is telling you the universe is not eternal. But if the universe had a beginning, then we are allowed to ask the next question. When? How long ago did the light first start traveling? How old is everything? And the answer to that turns out to connect, at last, to the faint warmth we left behind in the cold. Because the same beginning that keeps the sky dark also left something behind. A glow. The one I asked you to remember. It is time to bring the two halves of the night together. If the universe had a beginning, then it has an age. And we know it, now, with real precision. The universe is about 13.8 billion years old. 13.8 billion years since the beginning of everything. It is a number so large it slides right off the mind. So let me try to make it mean something. If you compress the entire history of the universe into a single year, with the beginning on the 1st of January, then all of recorded human history, every pharaoh and empire and war and love story ever written down, would fit into the last few seconds before midnight on the 31st of December. That is how young we are, against the age of the whole. But 13.8 billion years, vast as it is still finite. It is a specific length of time, and that finiteness is the key that unlocks the dark sky. Because light, for all its speed, takes time to travel. And in 13.8 billion years, light can only have traveled so far. This gives us something strange and profound. There is a distance, out in every direction, beyond which the light simply has not had time to reach us yet. A boundary, not in space itself, but in what we are able to see. We call it the cosmic horizon, or the edge of the observable universe. I want to be careful here because this is easy to misunderstand. The horizon is not a wall. There is no barrier out there, no edge to the universe itself. The universe very likely goes on far beyond it, possibly forever. The horizon is simply the distance that light has been able to cross in the time since the beginning. Beyond it, there are surely more stars, more galaxies, more light, but that light is still on its way. It has not arrived. It has not had 13.8 billion years to reach us, because nothing has. Think of it like standing in a fog at dawn. You are not at the edge of the world. The world goes on, but you can only see out to a certain distance, where the fog closes in. And beyond that, the landscape exists, but is hidden from you. The cosmic horizon is like that, except the fog is not fog. It is time. It is the simple fact that light beyond a certain distance has not yet had long enough to get here. There is a lovely wrinkle here that catches almost everyone off guard. You might think that if the universe is 13.8 billion years old, then the farthest we could possibly see is 13.8 billion light years, the distance light could cross in that time. But the observable universe is actually far larger than that, something like 93 billion light years from one side to the other. How can we see things farther away than light could ever have traveled? Because while that ancient light was crossing space toward us, space itself was expanding, carrying its source ever farther away as the light came. The light set out from somewhere that was close, and arrived from somewhere that is now enormously distant, stretched apart by the swelling of the universe during the long journey. So the bubble of everything we can see is some 93 billion light years across, and every single year it grows a little wider, as light from just beyond the edge finally completes its crossing and arrives for the very first time. And this is exactly what Poe imagined, and Kelvin proved. The dark patches in the night sky, the black between the stars, are the directions in which the nearest star along that line of sight is so far away that its light has not yet arrived. The line of sight really does, eventually, end on a star, just as the paradox said. But that star is beyond the horizon. Its light is still crossing the gulf toward us. And so, for now, and perhaps for a very long time, that direction stays dark. The night sky is dark because the universe is young enough that most of its light is still in transit. Every dark patch overhead is a place whose starlight has not yet had time to reach your eye. The darkness is not absence. It is delay. It is the universe being too young for its own light to have filled it. There is something genuinely beautiful in it. When you look up at the black between the stars, you are not looking at nothing. You are looking at light that is on its way. Photons that left distant stars long ago and are still, at this very moment, racing across the dark toward you, and will arrive, some of them, long after you and I are gone. The night sky is not empty. It is a work in progress. It is a room slowly filling with light that has not finished arriving. There is a companion idea here that I find just as moving, and it follows from the very same fact that light takes time to travel. When you look out into space, you are always looking into the past. The sunlight on your face left the sun 8 minutes ago. You never see the sun as it is now, only as it was. The nearest bright star you can pick out tonight, you see as it was years ago. A distant galaxy you see as it was millions or billions of years ago. Its light, a message sent out long before there was anyone here to receive it. Look far enough, and you are seeing light that set out before the earth existed, before the sun existed. To look deep into space is to look deep into time, back toward the beginning. And the deepest, oldest thing we can see, at the very edge of what is visible, is the moment the universe first became clear, 13 billion years ago, the ancient light we will finally arrive at by the end of tonight. And here is where it connects back to the other half of tonight, at last. Because if the universe had a beginning, then everything was different near that beginning. Wind the clock back, run the whole 13.8 billion years in reverse, and everything that is now spread out and cold and dark comes rushing back together, denser and hotter the closer you get to the start. The early universe was not the cold, empty dark we know now. It was the opposite. It was hot, unimaginably hot, and dense, and filled everywhere with light. Go back far enough and the entire universe was a blazing fire. Not a fire in a place, with darkness around it. The fire was everything, everywhere, all at once. Every point in space glowing white-hot, packed with light, hotter than the inside of any star. I find it almost impossible to picture properly, and I think that is the honest response. There was no outside to it, no dark surrounding a bright center, no edge you could stand back from and look at. The fire was the whole of existence. Space itself was smaller, everything crowded close, and every direction you could have looked was a wall of blinding light, because there was light everywhere and darkness nowhere. The universe did not begin in a dark void with a flash somewhere inside it. It began as the flash, filling everything there was. The dark came later as the light spread thin. Now think about what happens to that fire as the universe ages and expands. It does not go out. It cannot go out, not really. That much light and energy does not simply vanish. Instead, it spreads. As the universe grows, that primordial fire gets stretched thinner and thinner, cooler and cooler, spread across more and more space. But it is still there. It never left. It is still soaking through every corner of the cosmos, everywhere, in every direction. It has just cooled down. Over 13.8 billion years of expansion, that original blazing fire has cooled all the way down to a faint, even whisper of warmth, to about 2.7 degrees above absolute zero. There it is. Do you feel the two halves of the night clicking together? The faint glow that fills all of space, the one that holds the empty void at 2.7 degrees and will not let anything get colder. The warmth with no obvious source that I asked you, an hour ago, to please remember. That glow is the cooled down light of the beginning. It is the fire of the young universe, stretched and chilled by 13 billion years of expansion, still filling everything, still glowing, ever so faintly, in every direction at once. The thing that keeps space from reaching absolute zero, and the thing the dark sky was pointing to all along, are the same thing, the same fact. The universe had a hot, bright beginning a finite time ago, and that single fact keeps the night dark and the void warm, both at once. The darkness of the sky told us the universe is young, and because it is young, it once was hot and full of light, and that light is still here, cooled to a whisper, holding the cold at 2.7 degrees. One beginning, two mysteries, one answer. It took us a long time to be able to say that sentence, and it still gives me a small shock every time. Two of the plainest facts about the night, the kind you would teach a child, and they turn out to be the same fact, and that fact is the birth of the universe. There is something humbling in it. The cosmos wrote the story of its own beginning across the whole sky, in the dark and in the cold, and left it there in plain sight, all around us, every night, waiting for someone to learn how to read it. But I have been speaking as if we simply know all this, as if we could just reason our way to a fire at the dawn of time. And reasoning gets you close. Poe reasoned his way to the finite age. Kelvin reasoned his way to the proof. But the fire itself, the actual afterglow, the real warmth still soaking through space, that is not something we merely worked out on paper. We found it. We actually detected it. Two men, with a horn-shaped antenna in a field in New Jersey, stumbled straight into the light of the beginning, without even knowing what they were looking for, and spent a year trying to scrub it away as an annoyance, before they realized what they had. That story is one of the best in all of science, and it is where we are going next. To tell this properly, I need to give you one more piece of physics, and it is a lovely one. It is the reason the fire of the beginning cooled instead of just fading, and it is called redshift. When we say the universe is expanding, it is tempting to picture the galaxies flying apart through space, like debris from an explosion. But that is not quite right. It is space itself that is stretching. The galaxies are not so much rushing away through space as being carried apart by the swelling of the space between them, like raisins in a rising loaf of bread, each one drifting away from all the others as the dough expands around them all. Now think about a wave of light traveling through that expanding space. As the space it is crossing stretches, the light wave gets stretched too. Its wavelength grows longer. And for light, a longer wavelength means a shift toward the red end of the spectrum, and beyond. Redder, and then into the infrared, and then, if it is stretched enough, all the way into microwaves and radio waves, far below anything the eye can see. This is redshift, and it does two things at once. It is why the light of very distant galaxies arrives reddened and dimmed, and it is why the fire of the young universe, that blazing light that once filled everything, did not simply stay bright. As the universe expanded, every wave of that primordial light was stretched and stretched and stretched. Its energy drained away into ever longer wavelengths, until the blinding white fire of the beginning had cooled into a faint glow of microwaves. The same light, just stretched almost beyond recognition. So let me now tell you what that fire actually was, and when it was set free. For the first few 100,000 years after the beginning, the universe was so hot and dense that it was not transparent. It was a glowing fog of raw particles, so thick with energy that light could not travel freely through it. It was absorbed and scattered again the instant it was emitted, trapped, unable to get anywhere. The whole universe was an opaque, blazing fog. And then, when the universe was about 380,000 years old, it had expanded and cooled just enough for something decisive to happen. The temperature dropped to around 3,000 degrees, cool enough for the particles to settle into the first stable atoms. And the moment that happened, the fog cleared. Suddenly, for the first time, light could travel freely. All that trapped radiation was set loose in an instant, streaming out across a universe that had just become transparent. It is sometimes called the moment of last scattering. The instant the light stopped being trapped and set out on its long, free journey. Every photon of the cosmic microwave background that we catch today has been traveling, untouched, in a straight line ever since that moment, for 13.8 billion years. It is the oldest thing anyone will ever see, older than any star, any galaxy, any planet. When it set out, there was not yet a single star anywhere in existence. That light has been traveling ever since. For 13.8 billion years, it has been crossing space in every direction. And all that time, the expanding universe has been stretching it, redshifting it, cooling it. It began as the glow of a 3,000-degree fire. Stretched by a factor of more than 1,000 over all those billions of years, it has cooled to just 2.7 degrees above absolute zero. Its light shifted all the way down into the microwave band. We call it the cosmic microwave background, and it is, quite literally, the oldest light in the universe. The flash of the moment the cosmos became clear, still arriving, from every direction, right now. It is the faint glow that holds the void at 2.7 degrees. It is the reason empty space cannot reach absolute zero. It is the afterglow of the beginning, filling all of space, and it has been the answer to the cold this entire time. And that strange sameness we noticed earlier, the way the emptiness reads back the very same temperature whichever way you turn, was the clue all along. Only something that filled every part of space at the very same instant, at the very beginning, could possibly be that uniform. The evenness of the cold was the fingerprint of a single shared origin, printed across the whole sky. And now for the story of how we found it. Because we did not go looking for it. We tripped over it. In 1964, two young radio astronomers named Penzias and Robert Wilson were working at Bell Laboratories in New Jersey, using a big horn-shaped antenna to study faint radio signals from space. And they had a problem. No matter where they pointed the antenna, no matter the time of day or the season, they picked up a faint, steady hiss, a persistent background noise that would not go away. They were meticulous, and they were annoyed. They assumed it was a fault in their equipment, and they set about hunting it down. They checked every wire and connection. They ruled out interference from the city, from the military, from the atmosphere, and they discovered that a pair of pigeons had been roosting inside the great horn of the antenna, leaving behind what the reports of the time politely called a white dielectric material. They evicted the pigeons. They cleaned the antenna out, and still the hiss remained, coming from every direction in the sky, exactly the same everywhere they looked. They had no idea what it was. It was just an irritation, a noise fouling their real experiment, and they spent the better part of a year trying to get rid of it. And all the while, only a short distance away, at Princeton, a team of physicists was working out that if the universe had begun in a hot, dense state, there should be a faint afterglow left over, cooled by the expansion of the universe to just a few degrees above absolute zero, glowing in the microwave band, coming from every direction in the sky. They were, quite literally, building an instrument to look for it. When the two groups finally learned of each other, the pieces fell into place. The annoying hiss that Penzias and Wilson could not get rid of, the noise from every direction that no amount of cleaning would remove, was the thing the Princeton team was hunting for. It was the afterglow of the beginning. It was the light of the young universe, cooled for 13 billion years, arriving at last in a radio antenna in New Jersey, mistaken at first for pigeon mess and faulty wiring. They had detected the oldest light in existence by accident and had tried to scrub it off their equipment. For that discovery, Penzias and Wilson received the Nobel Prize in Physics in 1978. And ever since, we have been able to point instruments at the sky and read that ancient glow in extraordinary detail, mapping the faint warmth of the beginning across the whole sky. It is, without exaggeration, one of the most important things humanity has ever found. And we did not stop at simply detecting it. In the decades that followed, we sent spacecraft to map that ancient glow across the whole sky in finer and finer detail. A satellite called COBE in 1992 made the first real map and found something wonderful. The glow is not perfectly smooth. It carries the faintest ripples, tiny variations in temperature, no more than about 1 part in 100,000, a hair warmer here, a hair cooler there, by the smallest imaginable amount. Later missions mapped those ripples with breathtaking precision. And those ripples are not noise. They are the seeds. The very slightly denser patches in that infant fire are the places where gravity would, over billions of years, slowly gather matter together into the first galaxies, the great cosmic web, and eventually the stars, the worlds, and us. When we look at a map of the cosmic microwave background, we are looking at the blueprint of everything that would ever exist, printed onto the sky when the universe was 380,000 years old. The oldest light there is carries, written into it, the pattern of the whole future. Now let me bring it all the way home, because this is the moment the whole night comes together. The sky is dark at night because the universe is young, and the light of the farthest stars has not yet had time to arrive. That is the resolution of the paradox. The darkness is delay. But the sky is not entirely dark. It only looks dark to us, because filling every part of it, coming from every direction, is the cosmic microwave background, the afterglow of the beginning. In a very real sense, Olbers was right after all. The whole sky is glowing, uniformly, on every side, exactly as the paradox demanded. It is just that the glow has been redshifted by the expansion of the universe out of the visible light our eyes can see, and down into microwaves we cannot. The blazing wall of light that the paradox predicted is really there. We simply cannot see it, because time has stretched it into invisibility. Sit with that for a moment. The night sky is dark to your eyes, and blazing in microwaves, and both are true, and they are the same fact. The sky is dark because the universe is young, and the sky is secretly glowing because the universe was once, when it was young, on fire. The darkness and the hidden glow are two faces of one beginning. And that same glow, that same cooled fire, is what holds the empty void at 2.7 degrees and will not let the cold go any lower. The warmth in the emptiness and the darkness in the sky are not two mysteries. They never were. They are one thing, seen from two sides. The afterglow of the moment the universe was born. Remember the coldest place in the universe, the Boomerang Nebula, the one spot that managed to get below 2.7 degrees? Now you can see what it really did. It did not just beat empty space. It got colder than the afterglow of creation itself. It spent the fury of a dying star to chill one small patch of gas below the temperature of the oldest light there is. That is why it is so extraordinary and so rare. Everywhere else in the universe, the fire of the beginning still sets the floor. Two ordinary facts, the kind a child could tell you. The sky is dark, space is cold, and underneath both of them, the same profound truth. That everything had a beginning, a hot and brilliant beginning, 13.8 billion years ago, and that its light is with us still, keeping the void warm and the night, for now, only apparently dark. There is just one more thing I want to show you before we let the night close. Because that word, dark, deserves a second look. We have solved the paradox. But I want to end by taking apart the very idea of darkness itself and showing you that the dark, the real dark, the dark you think you see when you look up, is not empty at all. Here is something worth remembering about your own eyes. They are extraordinary instruments, but they are also very nearly blind. All the light there is, all the radiation streaming through the universe, spans an enormous range. From radio waves as long as a mountain, through microwaves and infrared, up through the thin band of visible colors, and on into ultraviolet, X-rays, and gamma rays with wavelengths smaller than an atom. It is a vast spectrum, stretching across an almost unimaginable range, and your eyes can see one tiny slice of it. A narrow band, from about 400 to 700 billionths of a meter, the stretch we call visible light, running from red to violet. That is the whole of what you can see. Everything else, the entire rest of that immense spectrum, is invisible to you. If the full range of light were a piano keyboard stretching for miles, human vision would be a single octave near the middle. So when you look up at the night sky and call it dark, what you really mean is that it is dark in that one narrow octave your eyes happen to be tuned to. You are not seeing the darkness of the universe. You are seeing the darkness of a very particular, very narrow kind of light, the only kind you were built to detect. And in all the other kinds, the sky is not dark at all. Open your eyes to infrared, the warm glow of anything with a temperature, and the dark patches between the stars light up. Cool clouds of gas and dust that give off no visible light at all begin to glow softly, and behind them, distant galaxies whose light has been redshifted out of the visible band shine through. In the infrared, the sky is crowded and warm and full. Open your eyes to microwaves, and the entire sky lights up evenly, everywhere, with the faint uniform glow of the cosmic microwave background, the afterglow of the beginning we just spent so long chasing. In microwaves, there is no darkness anywhere. The whole sky shines, gently, from every direction, the way Olbers thought it should. Open your eyes to X-rays, and you would see the sky studded with the fierce, hot breath of matter falling into black holes and the million-degree gas that pools between the galaxies. Open them to radio waves, and you would see vast glowing jets streaming out from the hearts of distant galaxies, structures larger than anything the visible sky reveals. In every one of these lights, the dark sky is not dark. It is alive with things our eyes were simply never made to catch. We have built eyes for every one of these hidden colors, great telescopes in space that see in infrared and can peer straight through the dark and the dust to galaxies so distant and so stretched by redshift that no ordinary telescope could ever find them. Observatories that map the sky in X-rays, watching matter scream as it spirals into black holes. Enormous arrays of dishes spread across whole deserts, listening to the radio universe. And, most wonderful of all, we have learned to sense the sky in a way that is not light at all. In 2017, instruments on Earth felt the actual trembling of space itself, ripples in the fabric of the universe set off by two neutron stars colliding, more than 100 million light-years away. Within about 2 seconds, an orbiting telescope caught a burst of high-energy light from the same event. And some hours later, once that patch of sky had turned into view, telescopes on the ground found the visible glow of the collision itself, a slowly fading light we call a kilonova. For the first time, we had witnessed a single event in the heavens both as light and as a shudder in the very shape of space. The dark, it turns out, is not only full of colors we cannot see, it is full of messages arriving in forms we have only just learned how to feel at all. Think about what that does to the word empty. We look up, see a few thousand stars and a great deal of black, and call space empty. But that same sky, to the right instrument, is pouring out infrared from every cool cloud and distant galaxy, glowing evenly in microwaves with the light of the beginning, flickering in X-rays around black holes, humming in radio from the hearts of galaxies, and trembling, now and then, with ripples in the very shape of space. There is not a single direction you can point that is truly silent. The emptiness is one of the busiest, most crowded, most talkative places there is. We simply happen to evolve eyes tuned to one thin, quiet channel of it, and mistook our own narrowness for the silence of the universe. With those infrared eyes, we have now looked back almost to the beginning of the stars themselves, finding galaxies that formed only a few 100 million years after the universe became clear. Their light so stretched by its long journey that it slipped entirely out of the visible range before it ever reached us. To our own eyes, that light is not there at all. The galaxies that first lit up the young universe hang, for us, in what looks like perfectly empty black. The first light of the first stars is streaming through you right now, and you cannot feel it. And it took us until this very decade to build something that could. So the darkness overhead was never really out there. It was, in a sense, in us, in the narrowness of our own vision. The universe is pouring light through us from every side, all the time, in 100 forms we cannot see, and we stand under that torrent and call it a dark and empty night, because the one small window we look through happens to be quiet. And I think that is the thought I most want to leave you with tonight, because it turns the whole story gentle. We began with two things that felt cold and lonely and a little frightening. A sky that should blaze but is dark, a void that the sun cannot warm. The stuff of that competitor's word, terrifying. The indifferent emptiness. The cold that does not care. But look at where we have ended up. The darkness of the night is not emptiness, it is youth. It is a universe so young that its light is still arriving. A night sky that is quietly, endlessly filling with light that has not finished its journey. The cold of space is not some hostile force. It is the simple loneliness of a place with too little in it to carry warmth, held gently above absolute zero by the leftover glow of the moment everything began. And the dark you see when you look up is not the absence of light. It is the presence of light your eyes were never built to see. A whole sky ablaze in colors beyond your window. Nothing about it is empty. Nothing about it is truly cold or truly dark. Those were only ever the names we gave to the small part of it we could sense. And here is the last turn, the one I keep coming back to. You are not out there in the cold. You are here. You are lying somewhere warm, on a small blue world wrapped in a thin skin of air that scatters the sunlight into blue and holds the warmth close, circling a steady star that has shone for 4.5 billion years and will shine for billions more. You are in one of the rare, lit, warm pockets of a young universe, a place where the light did arrive, where the warmth does gather, where there is enough stuff and enough shelter for a creature to lie still and wonder about the dark. That is not the ordinary case. The ordinary case is the void, at 2.7 degrees, glowing faintly with an ancient light. The warmth you are feeling right now, the ordinary comfort of being warm enough and safe enough to grow sleepy, is the exception. It is the rare thing, and it is yours tonight. I think that is the real gift hidden inside these two cold, dark facts. Not fear, but perspective. The default state of the universe is the empty void, at just under 3 degrees above absolute zero, dark to human eyes, glowing ever so faintly with the leftover light of its own birth. That is what almost everywhere, almost always, is like. And then there are these rare, improbable places, warm and lit and sheltered, where a star has gathered a little matter around itself and held it close and poured out steady warmth for billions of years, long enough for that warmth to become oceans and air and forests, and eventually a creature that could lie awake and wonder about the very cold it is being spared. You are one of those creatures, in one of those places, on one of those nights. The dark and the cold are the rule. You and this warm, quiet room are the exception. The furnace of the sun is cold at a distance, and the crowded sky is dark to our eyes, and yet here you are, warm and awake, or nearly asleep, held in the one place where it all came together, made of atoms that were forged inside stars, warmed by a fire 93 million miles away, under a sky quietly filling with light that left its stars before there were any people to wait for it. None of it had to turn out this way. The matter could have stayed thin and scattered and cold, the way almost all of it did. But here, in this one small place, it gathered and settled and caught the light and grew warm and slowly woke up and began to wonder about the dark it had come from. That is what you are, in the end. That is what tonight is. The universe, in one of its rare warm corners, lying still for a while, quietly wondering about the cold. So let the darkness be what it really is, not a threat, not an emptiness, just the young, patient, light-filled night, doing what it has always done, holding its ancient glow in every direction, waiting without any hurry at all for the rest of the light to arrive. There is nothing out there to fear. There never was. Only a universe so large and so young that its brightness has not caught up with itself yet, and a small, warm world where, for a little while, you get to lie still inside all of it and simply be here. Let your breathing slow. Let the day go. You are warm and you are safe, and the cold and the dark are only very old, very gentle light, still on its way. Rest easy. Sleep well. Good night.